All right, so we're working through some of your sample problems on your computer in section 4.3. So continuing on what we talked about earlier, you've got I'm picking up on number 10, very similar to the one we just did. I probably should have given you something a little more different to practice, but anyways, very similar to what we just did. So we're going to do log base 10, expand it. So we'll write log base 10 of the 3, and we're expanding each individual part of this. And do you see that the 3 and the x are individual pieces? That's a 3 times an x, even though you don't see the times. It is understood to be there. When we do times, we put a plus. So times and plus go together with logs and exponents. Then we carry the base over each time, log base 10 of the x. Then because of the divide, we write minus. And then we write log base 10 again, this time of the 13. So that would be our expanded form. All right, I'm going to skip over because there was a lot just kind of similar there. I'm going to skip down to number 14. And number 14, it says solve this equation. So this is understanding of a log. A log means an exponent, just another way of writing an exponent. It means this base to that power equals that number. So 5 raised to the third equals what? It's what it's saying. 5 to the third equals what? And you can do that on your calculator and get 125. So x is 125 there. Number 15, we go back to graphing. So in graphing, some of these you can actually, they're multiple choice or you can graph them yourself, but a lot are computer generated and they use the shifting rules. And this one, the next couple I think are. So to figure this out, you first of all click on the little icon, graphing icon, pull up the graph, and blows that up. And then you need to pick up the shape. They may have a parabola, a line. I hope you know these aren't parabolas or lines, and various shapes. So you do need to know the shape, and the log shape is this looking figure, that kind of curve. It is the inverse of the exponential curve. So the log shape, you click on that, and then you click back over here, and you just click anywhere because it will not let you position it where you want it. It only draws it in standard form. So it will draw it in standard form on your graph. Standard form goes through the point 1, 0 before any shiftings. Then we need to know what is up as 1. So there will be some boxes show up that look this. There'll be a vertical stretch box, a stretch box. Those happen when you have a multiplier in front of your function. We don't have that here. Then there'll be a vertical shift and a horizontal shift box, and an X reflection and a Y reflection box. All right, so you just need to pick what's happening here. What are your shifting rules? When you have a standalone add or subtract at the end of a function, that's always a vertical, and it's a shift, not a stretch. Shifts. It actually picks the graph up and moves it up one place. So you'll click that, and that is all that you click on this one. That's the only thing happening new. It is a base 3 log, and the computer already knows that and draws it accordingly. It has that in, if it says base, if it has that written in, don't change that because it already has it programmed. Just know that's a vertical stretch. That's it and that's all. Same thing on number 16. This is a log shape, even though it's a fraction base, and we know that, hopefully you know that, that makes it come downhill. It flips it as a downhill graph. It's still the same shape, so just click on that shape, and it will draw it in its standard form. Again, because it is a fraction base, it is a decreasing function, so it will come downhill instead. But again, the pivotal point of a log function is the point 1, 0, and let's shift it. Then we need to know the shifting rules here. If you have something grouped with your X, those are always your horizontal shifts, and horizontal shifts are opposite in sign. So instead of being -4 as it looks, you move it +4. So I wrote 5 and said 4. +4, and again, that's a horizontal, and it's a shifting. Remember, the stretches are when you have a multiplier in front of your function. Those stretch or affect the steepness of the curve. We're not seeing any of that in these examples yet. Okay, number 19, we have a double on this one. It has the graph we just did, the 1/2 shape. So again, you pick up your graphing tool, pick the curve, the log tool, and I think if you hover over it, it says it's a log tool. so you know it's a logarithmic shape. Then it draws it in its standard form for a fraction base, comes downhill, so it'll just draw it. Click anywhere, it just makes the graph in standard form. You cannot try to graph it where you think it belongs. Will not let you. Only draws it in standard form. Then you use the shifting rules that are given in the boxes to tell it where to shift it. So this is a horizontal shift, and again the word shift, not stretch, will be +1. The horizontal shifts are opposite in sign. And then this will be a vertical shift. The number on the end is the up and down movement, the vertical movement. Shift, 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 brought down. And then we need to distribute our half. So let me save that half to the very last thing. Log base 2 of 3. That 3 is brought down in front of that log base 2 of r. Oh, and this 5 also needs to come down, doesn't it? That any exponents come down as multipliers on the log. And then last, and some of the problems ask you to distribute the half and some leave it like that. Both are fine with me, but do kind of view the example and I'll tell you the form at once. Then we distribute the half. So 1/2 times 3 will be 3 over 2. And then 1/2 times 5 will be 5 over 2. And then that would be as expanded as you can get for that final answer. Just practicing with the log rules. Because we'll use them later to actually do something meaningful, because you might be saying, what in the world, why would I need to do that in the real life, maybe in Walmart, right? When will I do that? And you probably wouldn't. But when we do section 4.5, we solve equations, and they really do tie those equations well with some real life things that you might recognize and feel better about than this little exercise. But we're practicing this exercise in preparation for that, where we'll use these rules and solve equations. All right, so to encourage you. 22, we're going to go the other way. This is expanded form. Notice they're all base C, so they're all like base logs, and having like bases is pivotal to using these rules. But if you have a like base, you can condense or expand here. So here it's in expanded form. We're going to condense it to 1 log base C. M is given. Then minus n, so n is in the denominator, divide, and then another minus, so that is also divided in the denominator. So again, but when they're minus, they're divided, they're in the denominator. This one was just positive from the beginning, so it was in the numerator, and that's what we would type in. All right, last problem for this set, and then I think you'll have what you need, example of everything to do your homework. On 23, this always reminds me of 7th or 8th grade math class. I have this vague memory that we still had log tables in the back of our math books, and if you go to libraries or old bookstores, you might find texts like this. We used to have log tables of values in the back of our textbooks before everyone was assumed to have a calculator. So I'm just old enough to have just seen that, but most of my life I used a calculator. I'm not that old. But anyway, there were log tables, math book. Log base 10, which is the common log, and all calculators the common amount, so I could definitely type this on my calculator, but I'm just going to take you back to old school for just a minute. If you do log of 3 equals, notice it's exactly they gave us. If I do log of 5 equals 0.6990, again, there, or rounded to that. So I could definitely do this on my calculator, and I will never know if you do it that way. But take a moment with me here just to talk about how we could do this with a table of values. If they had, say, the first 100 values in the back of a math textbook, they would have all these written out, maybe the first 100. They couldn't have 1,000,000 or 1,000. They couldn't have all of the values. So what if we were trying to do log base 10 of 2,000? Might be a better example than this one that I've got generated out, because this one again is pretty small and it'd probably be on the table of values. But 150 probably wouldn't. You could figure out any type of log value base 10 based on just the first 100 by using these rules we just talked about. You could break down 15 and say 15 would be the same thing as 5 times 3. So if you only knew log base 10 of 3 and log base 10 of 5, you could find log base 10 of 15, because 15 can be thought of as 5 times 3. All right, 15 is 5 times 3. And because it's times, it would tell me I'm going to add those two log values. So all I'm going to do here is plus, add those together on your calculator or not. If you're doing it in the spirit of 1970 or whatever, then just add it by hand, and you'll get 1.1761. Now let's just check on our handy dandy calculator, and let's do log of 15 and see, yeah, it's about 1.1761. So same thing, you could get on your calculator, but just for the sake of argument. Let's say we were doing log base 10 of 200, something that shouldn't be on the table of values if you were doing it old school. So you could think log base 10 of 200 using the 5s and 3s, or you could break it down into times 1 and look up log base 10 of 2 and log 10 of, again, if it's multiply, you could add those together. I don't think I would with the 3 and the 5. I could do it partly with the 5, but anyway, you could break it down using these rules we've just talked about. Do a lot of the logs from knowing the property just talked about. We'll use it in a better way really in section 4.5, like I said, to do a lot of science, biology applications that I think maybe you'll like, and you'll say, I think I could see using that in these fields. Anyway, hope that helps.